Okay, 3:48. I think it's time to start. It's supposed to be 3:45. Okay, guys, here I am again, Gilberto Thomas, again present to you how to use the Adhesion Flex plugin in CC3D. The workshop, I'm not very sure if the workshop, this session is being live streaming right now, but for sure it's being recorded and it will be distributed afterwards. We thanks for the funding from this agency, which names are in the bottom of the slide over there. So let's start. What I'm trying to talk about today is to give you a little introduction about cell molecules, but just a basic one because I really don't know too much about that. What kinds of cell adhesion molecules you have, and then I will enter in the Adhesion Flex plugin and presenting one or two examples. But for sure, I will also give you a bonus to show you how to make movies from CompuCell3D and how to store the data from a simulation, from a run simulation. Okay, let's see. Well, in general, when we talk about cell adhesion in CompuCell3D, we are generalizing a very complicated mechanism, actually many different complicated mechanisms among cells and between cells and extracellular matrix. I mean, the cells can have adhesion between them, among them here, two cells with some different connections, and the cell with the extracellular matrix or any other substrate that the cell could be moving on. Okay, so we have then these images that are very different mechanisms for each one of those adhesions. Now we have to be clear that we have different families of adhesion molecules. So we have these integrins, chems, immunoglobulin family, selectins, and caderins. Caderins and selectins are calcium dependent, and the others are calcium independent molecules. Okay? And they can be heterophilic. I mean, the molecules adhere, one molecule, when it adheres with another molecule, which is different from it, or it can be homophilic, when the molecule adheres to another molecule equals to it. So the adhesion is quite a complicated mechanism, a process is involved in the cell membrane, actually. So, besides to having different kinds of cell molecules, adhesion molecules, the density of each one of those molecules can be different for each cell. And so it may connect in different ways. Okay? Our basic plugin in CC3D, which takes into account for contact energy, is for adhesion, is the contact plugin. In this plugin, there are no difference about what molecule is being considered in the model, and so both kinds of molecules, both kinds of cells in contact have the same number of molecules and the same type of molecule. Now, we are going to introduce you another plugin, which is called Adhesion Flex plugin. It is being described in the reference manual, CC3D reference manual, in the documental part of the web page, and it has this expression here. Remember, comparing with the contact plugin, the term in between parentheses here would be the J's between two different cells, two different kinds of cells. Now we are opening the J to explicitly say that each J has its own configuration. I mean, each J belongs to a specific adhesion molecule. N would be the density of a molecule, type M, and Nm, another molecule, a different one. It can be in same cells, likewise cells, the same type cells, or different type cells. See? Because we can now say that a single cell may have any number of molecules you want. We can say that the cell has cadarins, selectins, and integrins, for example. And each interaction between cell-cell equals or cell-cell different kind of cells will be, how to say, according with this expression there. See, there is this, let me go to the next slide. I think it's going to be better to understand. See, this is the expression. The parenthesis is the new expression for the J's. So Kmn is the strength of the interaction between the function of cadherin 1, molecule 1 and molecule 2. This delta Kronecker function here is the same as before. It is just to avoid changing inside the same cell. Okay? F and M is the function that convert the densities in contact energy. See, it's inside the parentheses. The parentheses is the new J. Okay? If you have n equal to m, I'm talking of the same molecules inside inside the same cell. If I have different m and n, I have different molecules. Okay. The number of this that will be included in this n function here is trying to reproduce the amount of molecules that a cell has in its surface. So let's see if you have some.
Should I interject a quick question?
Yes.
I'm privileged since I'm the host now. Can you go back to the previous slide?
The previous one? Yeah.
Yep.
My camera was not shown me because I have to move it a little bit aside because I have two screens and one covers the other. Sorry about that. Let me go back to the previous screen here.
Okay, so in that main equation,
this one. Oh, sorry.
This one. In the main equation there, in the large parentheses in the center, and you have capital N sub m and capital N sub n. In the parentheses there, should that be I and J? It's two different cells we're talking about.
Maybe I mistyped there. Yes, you're right.
And then down at the bottom, where it says
yes, because the external sum is in I and J. See.
And then down at the bottom, should it say N sub m and N sub n?
Yes.
Okay, I just want to make sure I'm understanding.
Yes. So I apologize. I have to do this very fast from yesterday to today.
No, that's okay. If I can echo back what I think this equation means.
Just because in the text here, it's M and N. See here.
Yeah. So if I can echo back, I would just want to make sure that I understand this. In those inner parentheses in the equation, the second sigma, we're summing over basically for each pair of pixels that are adjacent and that are interacting, one in cell I and one in cell J, we're then summing over all the pairs of molecules where one cell has molecule M and the other has molecule N.
I think, Sharon, this will be more clear to you when I show how the code appears to you.
Okay.
Okay. Let me go there. Another thing that this plugin allows you is to change the density of the molecules during inside the step-up, for example. If something happens in your simulation, an event changes the behavior or the state of the cell, you can change the density of the molecules with those calls that you can see in the screen there. You read the concentration here with this long command here, self-adhesion, flags, plugin, get, blah, 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 blah. Which cell, the ID of the cell, and which adhesion, which molecule you want to change. So in the next line, you're going to put self-adhesion, set adhesion molecule of that cell to a value which is going to be the new density after something has happened in their simulation. Okay, so the plugin is flexible also in this sense. Besides to define the different molecules, you can also change those values of the molecules during the simulation. Okay, let's see. The demo. The demo is in the student material folder. The complete code is there. I will go over the demo here on the screen, and later we can open it in the to edit and see it running in the player. Okay, so the beginning of the project is the same. You open the widget, make a new project, and for example, choose two cell species, dark and light, for example. I forgot a letter there. Interacting through two molecules. We'll call these molecules CAM1 and CAM2. And the cells are equally distributed in the blob initializer of radius 50. The grid can be 100 by 100 square grid, two-dimensional. We have to include the plugins now. See here, we do not include the contact anymore. We replace the contact by the adhesion flags. Sure. And the other ones are I forgot to click the surface, volume, surface, and center of mass. Those is a very simple simulation. Going ahead, inside the wizard, after you choose the adhesion flags, a new window opens for you to define which are the names of your molecules. Like you input the cells, remember, you say to include cell A and tape add. Here you input, you type the CAM1, click add, and it appears in the table of molecules in your model. It's very simple on the construction. So this is the code. Sorry. The left part is the basic stuff, the POTS part, the definition of the cell types, volume plugin, surface plugin, center of mass, and the adhesion flags. That was what I included in the wizard. These values here are already changed. I will explain later. And now in the right window, we have this adhesion flex plugin, how it looks like. Let's try to understand it now. I need to be. Okay. The initial part is the definition of the two molecules, adhesion molecule, Chem1, adhesion molecule, Chem2. Okay? The second part is which cell has which molecule with which density. So this is included by default from the wizard. Okay, this we can change the values. We can change for the values we want. But so here it says cell type D will have a density of 6.1 at the molecule Chem1. And the same cell, we have a density 4.1 for the molecule Chem2. Okay. For the other kind of cell, L, we have different values for Chem1 and Chem2. Those are the values, 2 and 3. Now, the next part here, I think it could be, let me show another one. I have more specific here. I forgot that. In this part, we have the definition of the interaction itself. So here is the formula. Remember that k factor in front of the function f that I said that it was the strength of the interaction. This is written here in this formula tag. You can put here any formula you want. Molecule. See, the function I'm using there now is that the interaction will be chosen by the minimum of the molecules. Who molecule has the smaller value between the two which are interacting at that time? Do you understand that, or was not very clear? Let's say you have one molecule here, one molecule here, okay, and the molecule of this one have 6, this one have 4. They interact. The interaction will be with the minimum number of molecules, I mean 4. It's like if you don't have receptors for the 6, you cannot attach 6 on 4. It's something like that. Okay? This is how the connection between the molecules are done. But you can change that. For example, multiply molecule 1 by molecule 2. I don't know. This part I don't understand. I let this for you. And here I am saying that when I interact molecule 1 with molecule 1, the strength is 0.25. Molecule 1 with molecule 2 is 0.5. And molecule 2 with molecule 2 is 25. So I'm giving weights for the different combinations between molecules. Is it clear?
So the formula applies globally to everything, but then each pair has its own weight.
Or say it again, please.
The formula.
The formula is for everyone.
For everyone, and then you multiply that by the weight for each pair.
Yes, yes.
Can you comment on what kind of expressions are allowed in XML? Because I'm never clear when I can put when you have to put a number in.
Here in the web page, I can let me go back a little bit. Maybe I can. I don't know if I can. No, I will. Just a second. I will show you here. I have this information here. I'm getting there. I'm going to put here. See, this is the web page for the help. Here, the syntax for the formula follow the syntax of the mu parser, which can be found in these others here.
Okay, great.
It's like a cosine of a number times cosine of another, any mathematical function, I think, the regular ones that can be used in Python directly. Okay. For example, I could write here molecule 1 times molecule 2. A multiplication sign for Python is an asterisk, isn't it? I think it is. So you could use their molecule 1 asterisk molecule 2, and then you have the product of both as a rule.
And it will always be a function of those two things, molecule 1 and molecule 2, and those are densities.
Yes.
And those are densities.
Yes.
Okay.
Okay. So, for example, if I have the interaction between D chem1 with D chem2, it would be 6 with 4. The minimum is 4 times 25, 0.25. It's going to be 1 in the sum, in the interaction of the sum in the expression.
Except the interaction will be between D and L, right?
No, it can be D and D. Why not?
Oh, if two cells of the same type are touching, right? Okay.
Yeah.
Got it.
We cannot interact with same cell inside the same cell. Okay, with same ID, but cell type, a cell ID type D, ID1 with ID2, we can interact. Understood?
So do we define a strength for CAM1 with CAM2 and also, oh yeah, I see now down below, all the pairs, CAM1, 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 CAM2.
Yes, all the combinations between the included CAMs here.
Perfect.
Okay. So I think now the code. Let's see if I can run the code here. I will open in my window and put over there. Give me 1 minute. Open projects. Oh, here to be. Here's the code. I should mention that took me a while to find the right numbers to get this thing working. What I'm going to show you is the cell sorting of the same cell sorting you use, which is very useful to see in CompuCell, the basic one made with contact energy. You can reproduce here without that plugin, but with this new plugin, only based in different of adhesions between different molecules. Okay, so I have to run from the beginning. The default values here are equals to everyone in the table, and we have to adjust by running the simulation till you get the correct factors. And I have the factors here. Okay. One thing, I will comment this surface energy term from the beginning for the first simulation run. Open in player. Where is that? Here. Here. Okay. I just clicked one step. Now I'm going to release the simulation. Oh, see, the cells kind of lose their identity. See, they become very, very wiggly or pixelized. Why? Because this plugin treats with negative energies. Remember there in the I will show you again here the expression, this minus sign here. This minus sign say that you are you are increasing negative energies, and negative energies in CompuCell make the cells fall apart. Then to prevent these things, we have to include this plugin, the surface energy, because the surface energy makes your cell stick, because they have to respect the length of the surface, I mean the perimeter. So the cell cannot be as wiggly as it wants. So let's do it here, new save. Now with the surface plugin included, I will stop this one and I will run. See, you have the cells much more similar to the old simulation. See, of course, you can improve the similarity with the cells from the square form, adjusting the parameters. But I really didn't have time to adjust it as perfect as I would like. But anyway, the sorting is happening. The dark cells, the blue ones, are going to inside, and the light cells are going outside. And you can compare now, analyze the table here. See, the dark cells have 6 for Chem1, and the L cell have 2 for Chem1. When they interact, they have the 2 factor, the minimum is 2, and the weight is minus 0.5. And the others have smaller values for interaction. So we can establish this boundary here between blue and the yellow cells to get the right situation for the sorting, right? No situation, but the right energies for the sorting. Okay, this is a matter of adjustments for those kinds of molecules. Of course, remember, if you have only J, it was a pain to adjust the energies at the beginning, if you have 2 or 3 cells involved. Now, if you have 2 kinds of cells and 3 kinds of molecules, it's a hard task to adjust everything. Okay, and in this interesting thing in this plugin, is that medium now can have molecules. You can say that medium has, for example, something like a extracellular matrix as adhesion, and the cell has another molecule, which is the integrin. So you can have the integrin from the cells interacting with the extracellular of the medium. Your model gets more complete in this way. Of course, a cost of much work in adjusting this these values. See, basically practically the sorting is already there. In the cable, if you want, you can play with values to see what happens if you change that thing there. Okay, let's go back to the presentation here. This is the final situation. Is that I already showed you? It's very fast. The final state, because the simulation is small, is about 45 cells, as you can read from the player here. It's very fast. Is that clear, or you need more explanation? I can try to explanation. Okay, Quirin, how do you spell your name? You say your name. Quirin is a French name? I will interpret. Let's say I have 3 molecules A and 2 molecules of B, and they bind one to one, and the number of events is, yeah, something like that, yes. Okay, so let's move on for another thing I would like to show you is this one. This is like a bonus for today, because I know that this plugin would be very fast. I decided to include this. It's not a tool, you know. Actually, is a tool is to save images. How do you save images? This is something you do in the player. How? See, when you open the simulation in the player for the first time, you click, for example, the step button once here, and the simulation will pause. After you then click in this small icon here, it's a photograph machine here once, and this click will create a kind of information about this window. I will show you later. Prepare the screen, the image saver to store the images you want. Okay, you have to press this button once, just once. If you change the view of the image here, for example, where is my player honey here? Let me show what I mean for that. I forgot to erase this. I will pause here. This simulation has paused here. I will click the button here. See? Screenshot, blah, 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 already exists. Why already exists? Because I this morning, I already clicking the button to make the slides for you. And I didn't change anything about in the view. In the image you are seeing here. Okay? When you click that button, information appears in the black window, CompuCell black window here. Let me give you some information that you cannot understand, actually. But it's there. You see the size of the window, probably, that is taking and is storing in some file that I will show where its file is. If I change here, for example, for this, I changed the view. I think this probably will now. It doesn't change. It only change if I have 3D. Sure. If I have a 3D, I can put this graph in a 3D. Where is it? 3D is no other window. For example, this is a 3D vision of that 2D simulation. Okay? I can move this here if you want. I think here it's gonna make a difference. See, now it didn't give me that warning that I already have information file, and I got a new one. So from now on, the image which will be saved will have this view here, a different angle of view. Okay, this is what we do when we press this button here. If you have more than one window, for example, remember that simulation I made with the flowing shell, flowing channel with 3 windows? I could have clicked in each photograph machine of each windows, and it will be prepared to save the 3 windows at the same time in different files, in different images. Okay, let me show you how. Come back these things. Okay, but this is not enough to save the image. Now we have to go to the CompuCell preferences. No, it's not preferences, it's configurations. I typed it wrong here. In the 2 options here, and these windows will appear. There is a line there, a box. You have to click to mark the box. Say, save image at every Monte Carlo steps. I choose here 500 Monte Carlo step. And save it. Click OK, and that's it. So you are ready to save images. Now you click your play button again, let the simulation run. What happens? So where are those files being created? The cell field, blah, 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 blah. It's a folder here, which is created when you start to save the images. The screen data folder below here is a folder which contains that file with the information about the view. Okay, they work together. Very well. So when the simulation runs, what happens inside this cell field folder, it became to be stored the image at each 500 Monte Carlo steps, the frequency I have chosen to save. Okay, so if your simulation has 1,000 Monte Carlo, no, 100,000 Monte Carlo steps, you have 200 files here, 200 images stored in this folder. Sure, understood? What the Python aspect of this module? I mean, sorry, Sharon, I didn't read your message. You mean the modifications of the values of the densities? Yeah, you could use that lines in the steppable file, as I put in the slides. Self get and set adhesion flags come for a specific cell, just like that. Okay, then go ahead. A second box. How to make movies. Well, now we have a bunch of images, and we want to do a sequence of images with that. I mean, we'll build a movie from that image. It's very easy. Okay. To make a movie, you can use any software you want that stick one image behind the other. sequentially, one of the other so far. And in Windows OS, there is a software that comes with the operational system, that is the video editor. So you open the video editor. Let me open the video editor here to show you. Did it open well? V. Here it is. Well, it is part of operational system. You type in the search box of your Windows and open the video editor. You start a new video project here. It's like this. New video. Pass. Give it a name. So you have here the window, and you have now I have to find where are the files, just to build a few. Let's see if they are here. Okay, they are the files. So first thing, show the details of this image. Why? Because in this way he puts in the crescent order of creation here, from the beginning to the end. Select all of them and drag to here. I don't need this window anymore. What? It doesn't go? Didn't go? Where is my file? Here. Oh, there they are. Everyone's there. The next step is to put these files in the storyboard here. They are all selected, and there they are. And the final step, or I mean, almost the final, is to say how much time each image should be shown. If you see, this number here is 3 seconds. It means that each image will be showed for 3 seconds of time, which is very long for a movie. See, if I play here, things gone forever to change that. Okay, so what I do is, let's select every one of these images here. This way, click Ctrl A, you select everyone, and here is the duration. You adjust the duration here, for example, 0.05 seconds each image. Give it enter. Let's see what's the. You have the accelerated mode. You see, there are a few images here, very little image, but The procedure is the same if we have 20 images or 1,000 images here. Then you go here, finish window, finish video, choose the quality. There are many qualities to save here. There are more options here if you want if you have a set of images that are very heavy, very complicated, and export. A window will be open and you save it. And immediately the video player of Windows will open with the complete movie. Is that clear? Now let me show the slides. I went over directly making the move for you, but everything is a slide. So if you want to follow the step by step, you have this option to watching the slideshow afterwards. Okay, every step is in here. Maybe not everyone, but the change of the duration time I forgot to include, but now you know. See the resulting movie for this long one here. This is a longer simulation that I did this morning with many images, and that's it. It's quite easy to make movies. You can another possibility is to use there is an older Microsoft software to make movies that was the old one called Movie Maker. It used to come with Windows 7, I think. Up to Windows 8, I think the Movie Maker was that. Anyway, go on. Second bonus. How to store data from CC3D. What do I mean for that? Show for Mac? Oh, I don't know. I don't have a Mac, Sharon. Sorry. Julio has. Ask Julio. But I'm sure that Mac has a video editor as well. Should be the same steps as this. Save data. In general, when you run a simulation, you want to store data. Because, for example, if you have a cell migration experiment, for example, you want to calculate, for example, the mean square displacements for a trajectory of a cell. How do you do that? You have to store the trajectory to process the data, and from that data analyze calculate the mean square displacement. Or if you want to know the velocity autocorrelated function for a cell, for a migrating cell, you also need to calculate the displacement and to calculate the speed between time intervals, and then calculate the autocorrelated function. So you most part of the time you need to store data to analyze later. Okay, and this is very simple to do. In the same file that we used now to create that cell sorting with the Adhesion Flex plugin, I duplicated it. I called it with a new name. Let me load it here. in the student's material module, it is written adhesion flex print. I put that. Okay, let's do it. This is made basically by hand. The CompuCell doesn't have any snippets to do that. And this is a Python program, you know. If you know Python, you know how to do that. The only thing is you have to be careful is with these things. First, let's say that you, for example, you want to track the surface and the volume of a specific cell in your simulation. Say that the cell ID number 40. So I explicitly define here a parameter that I call self ID 40, and the name of the cell that I want to follow. Okay. The second thing, actually, the 3 second things are this one. The first line here, which starts with dir, is the folder where the data, the file name with the data will be stored. This is a specific thing from CompuCell. Dir equals to self output underscore dir. Usually this output dir is the one in the user workspace. I will show you later. And then here I create a variable, which is a string variable, string kind of variable, see, which has the dir, I mean, where should be the file stored, and I will add to the name of the file the ID of the cell that I want to follow. See, the green part is text file. So I'm adding to this expression the phrase cell ID. Plus, I'm transforming the number 40 here in a string with this Python operator str here. Okay, so and this command will transform 40 number in 40 string, a word. And I'm including here in the name of the file, the output file, the size of the grid I'm working with. So I sum here a word grid size and sum to that part of the name the transformation of the length of the grid, self dim x, the dimension x of the cell, the grid. Since I'm working with a square grid, so this is the size of the square grid, 100 in this case. We show it later. So why we do that? Because now if you give a file a general name, sometimes you don't know what parameters you have been used to in that simulation. So for example, suppose you have a simulation where you want to change some quantity maybe 10 times for different values. And all the times, the data will be stored. So you have to write in the output file which thing is being changed in that simulation. You have to be able to identify your file with the parameters you are using in that specific simulation. Okay, This is why I usually, when I do my simulations, I build the simulation, the output file names using the data I'm running that set of runs. Okay. Okay. So once I have the name of the file number output here. Okay. I just to be more complete here, I have added to the name cell data, the term cell data dot dot. That can, because this dot the AT can be identified for any program, like, for example, Excel or Origin, those programs that make graphs, for example, or analysis of data sheets. So you use here the extension you want to be easily recognized for your software for processing the data. Okay, now at this line here, the file, I'm open the file that have the name self data, and this W after the comma, saying that I'm creating this file for the first time for writing. This is the only time that I use W when I open a file. I mean, I only use the W letter when I am creating the file. So once the file is created and open, I write something there. What I'm writing here, I'm writing the header of the columns that will be written in that file. Time is going to be the MCS, cell surface, and cell volume. Sure. And then I close that file. You always, in general, when you are running simulations, basically, I think in any language, when you are using output files to write data, the best politic is open, write, and close. Open, write, and close. Why? Because if you open once and run your simulation, if something happens with your simulation, the file will not be completely written, because the computer stores something in its buffer, and the writing part, it dumps the buffer from time to time. Not any time each time you say to write. So if you open, write, and close, the computer does the operation. Open, write, and close. If you not close, it keeps it to be written as long as it needs, or as long as its buffer is not completely full, and then it writes in the file. If you, for example, you could put the close here at the finish part of the simulation, called after the last Monte Carlo step. So the last Monte Carlo step was reached, then close the file. No, because if anything happens there, you lose everything you have done during the simulation. So open and close, always, okay? So now I have the file existing, and with headers. Now I have to write in them. This is where I write. In the step function, I run of the cells and pick the one I want to track, the cell ID, 40, remember? If cell ID is equal to 40, open the file, write MCS, the time, cell surface and cell volume, and close the file. Clear? How does it look like? This. Let me, I think, where should I think I have here. Here, see, just to see the names of the file. See, it added to default outputs. The default output, if you don't say anything to change the file name, the output file name, the output file name would stop here. Let me show you why then. Here. This would be the output file name. Is the simulation name with the date, Tuesday date, and the hour that the simulation has started. Since I add something, see, I added cell ID, number 40, grid size 100, plus cell data. So now if I, for example, if I come to the simulation and change the cell ID for 45, it will be, instead 40 here, it will be the cell ID 45. And then I know that I'm watching a different cell than the previous time. It's just a model, see? And the file is the file has this is stored this way: time, cell surface, cell volume. And here is the evolution of those quantities at each Monte Carlo step. Of course, you could change this frequency of written things in the file, adding here, for example, if Monte Carlo step is multiple of some quantity, maybe 100, each 100 Monte Carlo step, then you write. You can do whatever you want to say here. Is that clear? Is that useful for you? I hope it is. So that's all I have to show you today. It's not much, but I think there are useful things to use to use in your simulations to get more efficiency from the data you have, the images you got in the player. So it's important. I hope you have enjoyed this presentation.
There's a question in the chat.
However, it does not seem to be able to change binding factor. In the you mean in the Python? In the Python window? Well, I'm really not sure. It should be. Sorry, I'm not sure about that. I have to ask much, because since the CompuCell has changed to version 4, the commands have changed a lot. See this? Let's see if here in the manual page. You can also use it in the mitosis with the mitosis plugin. See, the child cell. And for the medium, yeah, it's a good question. I will try to find out and I will give an answer later, Quirin. Sorry. Did you find it in the? Oh, that's new. Oh yes, okay. And the yeah, I don't think it has in the. I cannot change now because I'm gonna mess with this thing. I would. Okay, I will try to see if there is this command in Python, and I'll let you know later. Okay. Thank you very much for your attention, guys.